All right, so we're going to pick up with confidence intervals today, but I've got the lecture slides in their folder. Two of the files that I think we'll look a little bit at today, but for sure the rest of this week we'll be using them, is this confidence intervals example file, and then this CI grade data. Okay, so confidence intervals CI. We'll be using those two files during the week. Today, if we hop into one, it'll most likely be this confidence intervals example. I'm not sure if we'll quite get that far, but pretty close. So last week I left off talking a little bit about confidence intervals and just introducing the idea, right? So we said what we were going to do was we were going to build our confidence interval around whatever sample mean we found. So ideally we'd like a population mean, but we usually don't have population data. We usually just have one sample, right? Now, if the population mean, let's say income is 50,000, well, then for my sample mean, I might see 54,000, I might see 48. It's very unlikely if I take a sample of 100 people, I'm going to see a sample mean of 200,000 if the true mean is 50,000, right? So probably the sample means I'm going to see are going to be somewhere close, but they could be a little off, right? So I'm going to build around that sample mean a range of values. So I'll have my lower and my upper bound. So this might be something like, I see a sample mean of 55,000, but I know if I see 55,000, it's very likely the population mean could be 52, could be 58. So I build an interval around that sample mean and say, well, with 90% confidence, I can say the population mean is somewhere between 50 and 60,000, right? I go 5,000 above, 5,000 below, and I create this range of values, right? Well, in my example, I just chose 5,000 arbitrarily, but there's a way in which we can ensure, or that we build our confidence intervals, we choose this W, and it's using some things we knew about that standard normal distribution. So I'm going to kind of review some of this, what we talked about last week, but the idea is, I'm trying to get a little bit better insight, I think. If this switches over to the dot cam, there we go. So if I'm thinking about, and I think this is my one that's dying. If I'm thinking about z-scores, right? And let's say I want to do something with 95% confidence, okay? So if I think about 95% confidence as a proportion, it's 0.95. So there is some z-score value such that the area in between the negative and the positive z-score is 0.95. Like there is a z-score that exists, right? I can try to figure this out. Well, if I have a symmetric distribution, then I know the area that's in the tails here would be 0.05. Or in each tail, I would have to have 0.025 in order to get 0.95 in the middle. Right? Now I'll show you, I'll look this up in the table here in a little bit, but if we know the area that we want in the tail, we can find the z-score that corresponds to that, okay? If I do that, I'll find that it's positive and negative 1.96 would give me 0.02 in each of those tails, or the probability of seeing something that's between 1.96 standard deviations above and below the mean, right? That's the interpretation of our z-scores. The probability that I see something 1.96 standard deviations above or below the mean, somewhere in that range, is 0.95. Right? 95% chance something is within 1.96 standard deviations of the mean. Okay? From there, what we can think about is, what do I know about the distribution of my sample means? Well, as long as I have a sample size over 30, they should be normally distributed, right? And they should be normally distributed around whatever that population mean is. Even if I can't see it, right? It exists, even if I don't have the data, I know my sample means would be normally distributed around it. Well, if I want to go 1.96 standard deviations away from this mean, what I'm really thinking about is, so here, I'm going 1.96 standard deviations below and 1.96 standard deviations above the mean. Right? So I'm looking at the standard deviation, right? I'm looking at the sample mean distribution. So when I'm thinking about the standard deviation, it's the standard deviation of my sample means that I'm going to the left and the right of. So if I think about everything that's kind of in this range, right? Let's say I see a sample mean that's right here. Okay? If I build my confidence interval around it such that I go 1.96 standard deviations below the sample mean that I saw, and then I go 1.96 standard deviations above that sample mean, notice anything in this range, right? Like if I had to put a guess on this, well, if this value is 1.96 standard deviations below, then this value is, I don't know, maybe about a standard deviation below, right? It's not near as far away from that mean. So let's say I, go over one standard deviation, but then remember, when I build my confidence interval, the value I'm adding to the, the amount that I'm going to the left and the right is 1.96. So if I go over 1, but then back 1.96, then this value is going to be past that population mean, right? So this confidence interval would include my population mean. And that's going to be true for any value that's less than 1.96 standard deviations away, right? Any sample mean I see here, when I go down and build this confidence interval around it, well, it's less than 1.96 standard deviations away. So when I add and subtract 1.96 standard deviations, I'm going to have an interval that I'm guaranteed to include that population mean. Okay? Now, if I see something way out here as a sample mean value, well, here, if this was the point where I was 1.96 standard deviations above, this is going to be like, I don't know, 2.5 or 3 standard deviations above, right? So now when I build my confidence interval, right, and I go 1.96 standard deviations below, and I'm not even going to draw this one because it doesn't necessarily matter, but right, we could build the upper bound as well. Well, notice if I go out 2.5 or 3 standard deviations away from that population mean, and then I go kind of back 1.96, and I probably didn't really draw this to scale. If I was really going to draw this to scale, it probably would be, somewhere out here. Well, if I go out 2.5, but then back 1.96, I'm not going to be back to that population mean. So these confidence intervals for values that are more than 1.96 standard deviations away aren't going to include that population mean. Okay, so that's the idea of what we're doing with confidence intervals. We only see one of these sample means. And so when I build that confidence interval, it's almost like I don't get to see the rest of this. But what I know is if I go 1.96 standard deviations above and below, there's a 95% chance I'm going to see one of the values in this range. Or, right, 1.96 standard deviations above and below, there's a 95% chance I see some sample mean, if I just take one sample that's in this range, and if I saw a sample mean in this range, its confidence interval would include that population mean. So if I just have one confidence interval, the chances that that interval includes the population mean, 95% chance based off of kind of using these z-scores, right? I mean, I'll explain a little bit more why it's 1.96 here, but if we want the 95% confidence interval, this will guarantee that 95% of the time, the confidence interval we build, it's going to be using a sample mean such that its confidence interval includes that population mean, but we'd be wrong 5% of the time. Right? That's why we're only saying it with like 95% confidence, because here we'd be wrong. If we just so happen to get this as our sample mean, our confidence interval wouldn't include the population mean. But we're only going to see these values, right, 5% of the time. Okay? So that's, oops, sorry, this is a little bit off. So that's kind of the setup, right? That's the general idea of what we're doing. Okay? Is there anything else I wanted to say at this point? I think I'm okay with it. So we'll go back here. And that's kind of, we talked a little bit about this last week, and I kind of should, but a little bit more elaborate with kind of what I showed you today. So this is kind of where we left off. I'm getting the screen to switch over in class. There we go. So that's what we just kind of worked through. So the next thing that we'll talk about is this term alpha, okay? So the example I just worked through was thinking about a 95% confidence interval, okay? So I'll put this up here and then try to have this guy here. So when we're thinking about a 95% confidence interval, you can think about the area that you want within the interval is 95%. That means the area you want outside the interval would be 5%, right? And if we're dealing with probabilities, okay, all right, what is this? All right, well, if we get interrupted, we know why. So 5% is outside the interval. In decimal form, right, the total area kind of in our tails here was 0.05, right? So the 95% confidence interval, 5% outside the interval. In decimal form, that's our alpha. That's what alpha represents, right? So it's not really the percent outside the interval, but it's the probability that we see something outside the interval, okay? So I can work in either direction. If you tell me, you know, I want the 99% confidence interval, well, that means there's 1% outside the interval. In decimal form, that's 0.01. All right. I don't want you to, okay. Guess I think Microsoft apps might be getting updated, so I guess that if these shut off on us, we'll know. Or I can work in the reverse, right? If you tell me alpha is 0.1, well, I know that means that there's probability of 0.1 outside my interval, so the probability I'm in the interval is 0.9. In percentage form, 90%, right? So alpha, we really, you know, kind of the non-technical way to talk about it is really, it's the kind of total area that you want in your tails, right? Total area, right? We've got two tails, that means half of alpha will be in each tail. Okay? So we're eventually going to get to this equation for the confidence interval. Now, in our example, we were using 1.96, but how did I find that? So why, instead of, you know, these values can change depending on the confidence interval we want to build, why does it look up the z-score that gives you alpha over 2 in the tail? Well, if you think about this, right? What was I doing up here? I wanted a 95% confidence interval, so the total area I wanted in the tails was 0.05. But it's a symmetric distribution. I want to use, you know, whatever z-score gives me half of alpha in each tail. So really, like negative 1.96, that was the z-score that gave me half of alpha in that lower tail, and then it would have been half of alpha in that upper tail as well, right? Because if the area to the left of negative 1.96 is 0.025, the area to the right of positive 1.96 is 0.025, right? It's a symmetric distribution when we're looking at the standard normal distribution around 0. Okay? So when we were building these confidence intervals down here, basically the setup we have was to get the lower bound, I'll subtract whatever z-score was giving me alpha over 2 in the tail times the standard deviation, right? Because this is telling me how many standard deviations away do I need to go? Well, if I need to go 2 standard deviations away, then I would take 2 and multiply by the standard deviation I need to go away from that mean from. Okay? So that's why we arrive at this equation here for our confidence interval, right? Take that sample mean you see, add to it this value to get your upper bound, and subtract this value from it to get your lower bound. So it's almost like this is kind of like 2 equations, right? One to get the upper bound, which is what you add. One to get the lower bound, which is when you subtract. Okay. Now, this isn't perfect or technically correct, but it's easier to speak about it in this term. Really, we should only be calling this the margin of error when we're dealing with proportions, but for the sake of what we're going to do, we're just going to reference this as our margin of error, right? The thing that we're adding and subtracting to our sample mean to build our lower and upper bound, we'll refer to that as the margin of error, okay? So, you know, we've got everything that we need. One thing that is a little different, and I'll rewrite that formula down for us because I want to show you another form that we can see. So this was just the equation I just had up on the screen, which is how we build our confidence intervals. However, we know that from last week and prior to last week, the standard deviation of our sample means is just the square root of the original variance divided by our sample size, right? This was the idea that when we take a higher sample size, it, you know, reduces the variance of our sample means or reduces the standard deviation of our sample means. So instead, you know, if we're working through these problems, I'll kind of go through a couple. you can calculate the intermediate value first, right? You can calculate that standard deviation and then plug it in, or I can just plug it into that formula and do it all at one time, right? Either way is fine. It's just one way I'm kind of doing an intermediate step. And I'll show you when we work through the problems why this sometimes, my preferred way for you to do it, and my preferred way that I like to work through these problems is using that intermediate value, because it just lets you visualize in the distribution and think about numbers that actually make sense a little bit more. If we plug everything in here, it's a little bit easier to make a mistake in your calculator and not be able to recognize it. So those are going to be the two kind of versions of the formula that we can use. So knowing that, right, what are some things that are going to change our confidence intervals? So I have them all outlined here, but I'm just going to talk through them and have the equation pulled up and kind of write some things down. And by the time we're done, we'll have this slide created. But I want to kind of build this slide essentially for you. So one of the first things that we can do is think about what's going to make this confidence interval wider or more narrow. Okay? So the first thing, let's say I want to go from 90 to 99% confidence. Right? So this is my confidence level I want. Okay? What's going to be the alpha values here? Well, for the 90% confidence interval, my alpha should be what? 0.1. Yeah, that's not too bad. For 99% level, alpha would be 0.01. So what's going to happen when I want to go to a essentially larger confidence interval means a smaller alpha value. Okay? So if I think about what I'm doing here, part of the process is looking up the z-score that gives me half of alpha in each tail, right? So what's that z-score that would give me, I guess, alpha over 2, so 0.1 over 2 here is 0.05 in each tail. Okay? That's going to be part of the process. Well, I can look that up, build my confidence interval. So then when I go to a 99% confidence level, what's going to happen? Well, now I don't want 0.05 in each tail. I'm going to want half of 0.01 in each tail. So what, 0.005? Well, if I want to get a smaller area in my tail, I know that I'm going to have to look at a z-score that's kind of larger in absolute value, right? The positive one would be larger, but the negative one technically would be smaller, right? A larger negative value. Okay? So if I'm using a larger negative value here, what's that going to do to my confidence interval? Well, if this goes up, my margin of error goes up. I'm adding and subtracting a larger amount to that sample mean. I'm going to get a wider confidence interval. So anytime we want to go increase the confidence level, that's going to give us a wider kind of confidence interval once we construct it. So higher level of confidence leads to a wider confidence interval. And that intuitively makes sense. If I tell you there's with 90% confidence, I can tell you the true mean income is between 50 and 60,000. Well, how can I tell you something with 99% confidence? Well, what if I just say, well, with 99% confidence, I can tell you it's between 40 and 70, right? I just make the interval wider, and I can tell you, with a higher level of confidence that it's somewhere in that range, right? So that's kind of intuitive, right? I walked through kind of the statistical reason why, but this is pretty intuitive. If I want to say something with a higher level of confidence, just give a bigger range of values, right? That's pretty easy. So the next one is one that we really just don't have a lot of influence over, but we can talk about what would happen for differences between data sets. So let's say the original variable that I'm sampling from, or the original data I'm sampling from, that the variance is higher. Well, if the variance is higher, what's going to happen to my confidence interval here? The variance or the standard deviation is higher. This goes up. I'm adding and subtracting a larger value to that sample mean. So I'm going to be getting a wider confidence interval there as well, right? So anytime that margin of error increases, right, I'm going to be getting a wider confidence interval. Now, what was the mechanism for that? Well, if the variance of the original data goes up here, and this represented my standard deviation of my sample means, well, if that numerator gets larger, then the entire fraction gets larger, right? So if the original variance goes up, the variance of the standard deviation of my sample means also goes up. But I don't have a lot of power over that. The variance of the data I'm sampling from just is what it is, right? Like if I'm looking at height, right, the variance of height just is what it is. The third thing that we have more control over is, what if we took a higher sample size? Okay? So if I take a higher sample size, and I accidentally marked right here, but let's say my sample size goes up. What's going to happen to the standard deviation of my sample means, this entire fraction? If my denominator gets larger, the fraction is going to get smaller, right? So if a higher sample size will reduce the standard deviation of my sample means, so my margin of error is going down. So if I'm adding and subtracting a smaller amount to that sample mean, my interval is actually going to be more narrow, right? So or smaller, I guess, if you want to think about it that way. Okay, so these are the three things that can kind of change in our confidence interval that will change the width of our confidence interval. And right, the end goal of all this is to get a very narrow confidence interval, because I'm trying to pinpoint down where that sample mean is. If I have a really big confidence interval, let's say I say the average income is somewhere between 40 and 80,000. Okay, yeah, I probably could have guessed that, right? Like that's not very helpful. But if I can say the average income is between 51 and 53,000, okay, now I've narrowed it down a lot more. So our end goal is to be able to try to narrow down this confidence interval. So essentially what we're doing is narrowing down where the true population mean could be. Okay? And the one way that we really can influence that, really narrow that down, is increasing our sample size. Right? That kind of makes sense. If I have a larger sample, it's going to be easier. You know, I have more information from the population. I can narrow down those range of values a little bit easier. All right. So, you know, I wanted to try to give us, you know, like I said, we're going to be using a lot of these principles for weeks, right? So I really want to make sure we have a very good understanding, right? So I guess, you know, if people aren't watching the YouTube videos, this falls on deaf ears, right? But it's okay if you're not showing up to class every time when you can, but make sure you're trying to get on and watch the Zoom. At the very least, watching those YouTubes, like not 3 weeks past the fact, right? I'm talking to you guys. I don't need to talk to you guys, right? But if you're watching this video and you haven't been kind of keeping up to date as much, I think in the first kind of third of the class that might have been a little easier to do. I highly suggest do not fall behind at this point, because 2 weeks down the road, you'll be like, we're at a completely different place, like, you know, than we are. So we are today. So let's say we have this birth data that we were working with last week, and I've got the length of the pregnancy, so the infant gestation, and somehow I know the population variance is 9 weeks. I can't see the population data, but somehow I know that throughout human history, you know, from all the data that's ever been collected, it looks like it's been about, you know, the variance is about 9 weeks. So I take a sample of 81 births, and I see that the average length of those pregnancies was 38 weeks. And I want to build a 95% confidence interval for what the true population mean is. Because even though my sample mean is 38, the true mean could be, I don't know, 37, could even be 40. And, you know, maybe if I'm thinking about, you know, I don't know, a doctor, someone who really wants to pinpoint down the kind of average time when you know, the birth is going to occur. So that's the setup. We want a 95% confidence interval, okay? So how do we set up one of these examples? Well, we were told that the variance, the original variance of the data we sampled from was 9, sample size of 81, and we know that the sample mean is 38. Okay? I wanted a 95% confidence interval, so what I'm thinking about is, okay, what z-score would give me, positive z-score here, alpha over 2 in each of these tails, all right? My alphas and 2's kind of look the same, but this is alpha divided by 2, right? So we wanted a 95% confidence interval, so we want the area in between those z-scores to be 0.95, means the area outside of them, 0.05, so my alpha here, right, is 0.05 for a 95% confidence interval. But then there's half of alpha in each tail, so 0.025. Well, I know that if I want 0.025 in each tail, right, that gives me a total of 0.05 in the tails, which is what I wanted. I'm looking at a standard normal distribution here, so I can go to my tables, right, and say, well, look, I know the area I want in the tail is 0.025. This is essentially when we were looking at the inverse transformation, right? We know the area in the tail, we want to find the z-score that would give that to us. So we don't look up the z-score using the row and column headings yet. We want the area in this tail to be 0.025, so we try to find that. So searching through here, looks like it's right there, 0.025 exactly. I go over, negative 1.96, okay? So negative 1.96 would be the z-score that gives me 0.025 in that lower left tail. And then positive 1.96 would be the z-score that gives me alpha over 2 or 0.025 in the upper right tail. But I only really had to look it up once, right? Once I knew the negative z value, the positive one's the same thing, just positive. It's the same value but positive. So we've got our z-score. From here, it's really just a matter of plugging these values into our equation. So so let's go take our sample mean. We've got this z-score for alpha over 2, which we know is 1.96, right? And then we multiply by the standard deviation of our sample means. Okay? So I've got this plugged in. I know that my sample mean is 38. From here, I've got an equation for the standard deviation of my sample means. So this is going to be what? The square root of 9 over 81 if I plug those values in, which I think works out to be about 1/3. Okay? So I can plug that value of 1/3 in, and now it's really just some pretty easy, computation of my calculator, which to get my upper bound, right, I would just take 38 plus that margin of error. And to get my lower bound, I would take 38 and subtract that margin of error. And I'm done. I now have my confidence interval. Whatever these two values are, with 95% confidence, I can say that the true mean is somewhere in between the lower and the upper bound that I calculated. Okay? Any questions on this before I keep going here? Now, what I could have done, I want to make sure you can still see this, but there we go. Oh. Instead of using this version of the formula, I could have said, well, look, I also know that I could plug in, like skip the intermediate step, and just plug everything into this equation, right? So my upper bound would be what? 38 plus 1.96 times the square root of 9 over 81. And then the lower bound is that exact same thing, but I'm subtracting my margin of error. Well, I can go ahead and do this computation. I'll get the exact same answers. It's just up here I calculated the intermediate step. And the reason why this is somewhat helpful is, well, look, if the standard deviation of my sample means is only 1/3, even if I'm going about 2 standard deviations above and below, I know that I'm not going to be very far away from 38 with my upper and lower bound, right? Because that standard deviation is pretty low. So when I'm adding and subtracting 2 or 1.96 standard deviations, the standard deviation is only 1/3. I'm not going very far to the left and right of that sample mean of 38. Now, I can't really necessarily see that as easily if I do it all in one form. Not, like I said, you can use either way. Either way is fine. If I'm doing this real quick and just want to get the answers, this is more than adequate. But here we kind of prevent us maybe from making some parentheses mistakes maybe in our calculator, or just personal preference, really, which way you want to do it. Okay. Any questions for me on that before we keep moving? Is there something else I wanted to point out here? Yeah.
So an exam, would you just ask if the upper and lower bound?
Yep, yeah. Either way, yeah, I'll just ask for the upper and lower bound, and it doesn't matter which way you do it. Either way is correct. Yep. Any other questions? Okay. All right, we're going to work through where we at in time. Okay, we're going real quick. So let me make sure I didn't forget anything here. I think we should be good. So we kind of already worked through all this, right? But we identified what we needed for that confidence interval equation. Using the alpha, and think about alpha over 2 in each tail, we found the z-score that would give us that desired alpha over 2 in each tail. We calculated that intermediate step. I showed you how also you could kind of skip step 3 if you really wanted to. And then it's just a matter of plugging everything into our confidence interval equation. So if you wouldn't have done step 3, you could have used this equation, which might look a little different than what I have written here. But remember that standard deviation of my sample means can be written 2 ways, because if I take the square root of something squared, that's just itself, right? So this is just a slightly different version of that confidence interval equation, right? I'll typically write them like this, but occasionally I'll have them in the slides, or maybe I'll work through an example using this form, because really you can use either one, right? If I know the standard deviation, I automatically know the variance. If I know the variance, I automatically know the standard deviation. Okay. So if we do this computation, we kind of get this in pretty narrow range where I can really narrow down where the population mean length of a pregnancy is within really about a week, right? I've only got kind of a week gap here. So the reason why is because I took a pretty high sample size, so that reduced my standard deviation of the sample means quite a bit. But also there wasn't a ton of variation in the original data, right? 9 weeks is the variance. I mean, it might sound like a lot, but in terms of just like, the distance, like 9, it's, if I look at the variance on income, it's in tens of thousands sometimes, right? So it is a relatively small variance compared to other examples. So we get a pretty narrow range. Okay? I'll save till the next example how we really interpret these ranges, but hopefully after the next one, I'll come back here and we'll think about how can we interpret this confidence interval we've constructed. I mean, we know that it's saying that with 95% confidence, the true mean is somewhere in this range, but what's really the usefulness of this? So I think in this next example, we really start to see the application of building confidence intervals. So it's kind of might seem like a dumb example, but I'll use it to show you how far-reaching this idea is. So let's say I go over to the rec center and they've got all these weight plates and they say they weigh 45 pounds, right? Well, I take 35 of them, I weigh them all, and I get a sample mean weight of 46.5, right? Well, the reason why is because the original production process has a variance of 25 pounds, right? So we think about, I don't know exactly how these are created. This is just the story. That makes sense, I think, to me and most people. If you're creating this product and it's made up of all these different metals, right? You're trying to get metals that weigh a certain amount to have a certain size plate, and you're trying to get the cheapest metals, right? So maybe in order to make it cheaply, I might use, I don't know, I'm assuming, I don't know if this is true, that, I don't know, magnesium is cheaper than iron, right? Or zinc, whatever. And so part of the plate is going to be made up of zinc, part of it's going to be made up of magnesium or all these other metals, so that I can do it the cost-effective way, but also have it this targeted weight. Well, if I'm using multiple metals, when I pour these into the molds, each one is not going to be the same, right? My products will have some variation to them. Okay? So this is the kind of setup. Well, the problem is if I don't have this kind of mixture, the proportions correctly, my mean plate might not actually be 45 pounds. But if I just see a sample mean of 46.5, it's very possible that the true mean still is 45. Right? So let's use the information we have with this idea in mind, and then we can start to think about how we can use the confidence interval we built to say whether or not this production process is actually creating the product it's trying to, which is a 45-pound weight plate on average. So we want to build a 90% confidence interval here. How did I know it was 90%? Well, if alpha is 0.1, that's the total area in my tails, or the area outside my interval. So the area in my interval would be 0.9, which has a percentage, 90%. Okay. So before we even go to the dot game here real quick, if I want alpha of 0.1, well, I guess maybe I will. I'm just not going to switch completely over. If I want an alpha of 0.1 in my tails, what I'm thinking about is if alpha is 0.1, each tail has alpha over 2, or 0.05 in each tail. Right? So I want, really what I'm saying there is the z-score that would give me alpha over 2 in each of these tails. And alpha over 2 happens to be 0.05. Okay? So move this. And so I'm trying to find 0.05 here, okay? Well, going through 0.005, so keep going. Oh, that's pretty close, 0.0595495, 0.0505. Okay, these are both equally as far from 0.05. So because we're constrained using this table to 2 decimals, this is where we have kind of a rule that will, a convention that we'll follow in this class. If I'm in between these two, right, 0.05 is in between 0.0505 and 0.0495, right? Then the z-score I need is going to be somewhere in between the z-scores that give me these 2 areas in the tail. So I go over negative 1.6, scroll up 4, and negative 1.65. Okay? So if I'm in between 2 values like that, I'll always take the larger of the 2 in absolute value, right? So if I'm looking at the negative value, right, negative 1.64, negative 1.65, I'll take negative 1.65. Essentially ignore the negative sign, ignore the sign, and just take the value that's higher in absolute terms. Okay? So I just looked up that z-score that would give me 0.05 in each tail, or half of alpha in each tail. Okay? Now, choosing the higher of the 2, just to kind of be complete in this explanation, we're erring on the side of caution, because technically the z-score I needed was somewhere in between 1.64 and 1.65. In fact, technically, if we go out to the 3rd decimal, it's actually exactly 1.645. But we were constrained to 2 decimals, so we didn't know that. Why do I know that? Because I've done enough of these and I work with a distribution enough. And also Excel can help me figure this out. Okay? But when we're only limited to 2 decimals, if I go out to the higher value, what area is technically going to be in that tail? Not 0.05, which this is the z-score that gives me exactly 0.05. When I go to negative 1.65, it was actually a little bit less, which means that when I'm saying something with 90% confidence here, I'm actually saying it with like 90.05%, or just a little bit more. So we're erring on the side of caution. Okay? All right, we don't need this because we're limited to 2 decimals. And from here, it's really just a matter of plugging our values in, right? We had the sample mean we saw was what, 46.5. The variance on the production process was 25. And our sample size was 35, right? So we go through. I'm going to show you how we would do it, calculating the intermediate value. So if I wanted the standard deviation of my sample means, that's the square root of the population of the variance I sampled from. So what, 25 over 35? And I think this is roughly, I guess I should put approximately here, 0.84. Okay. Well, now I have the standard deviation of my sample means. I know the z-score, and I have my sample mean. So it's just a matter of plugging my values into that equation. Okay. So I guess for my upper bound, I'll have what? 46.5 plus 1.65 times approximately 0.84. And then for the lower bound, that exact same thing, but I subtract my margin of error. Right? Now notice when I'm looking up that z-score, there really are 2 of them, right? Like it's a negative 1.65 and a positive. But that's already kind of built into my confidence interval equation, where when I add, I'm really using the positive z-score to get the upper bound. And when I subtract, I'm really using the negative z-score to get the lower bound. But once I have the value, I can essentially ignore the sign because that's already built into my confidence interval equation. Now notice the standard deviation is pretty low here, 0.84. So once again, I'm not going to have a very wide distribution or a very wide confidence interval. Any questions on that one? Okay, so if we actually do this math, these are the steps that we just kind of outlined. So that's the out 4 decimals. When we plug everything in, we get a lower bound of 45.11 and an upper bound of 47.89. Okay? So let me draw something before we switch over here so I have the numbers. 45.11, what was it, 47.89. So we have this confidence interval, and we built it around that sample mean, which was 46.5. So what I'm saying is that based off of the sample evidence I found, with 90% confidence, I can tell you that the true mean is somewhere in between 45.11 and 47.89. So the true population mean could be 46, could be, I don't know, 47.2. It's going to be about one of those values. With 90% confidence, I can tell you that. Now, if I think about what's interesting in this example, the value of 45, which is what this company desires its product to weigh on average, is not in that range of values. So I could go to this company and say, look, you say you're making this product and you're saying it weighs 45 pounds, but with 90% confidence, I can tell you you're wrong. On average, it doesn't, right? And that might seem really trivial when we're talking about weight plates, but if I'm talking about the weight of a steel beam that's supposed to support an entire floor of a building or something, well, that's a problem, right? Or if I'm producing some type of medication and I'm saying it has a certain dosage and I can turn that dosage into a weight, well then yeah, the weight really matters if the targeted weight isn't the weight that my product actually is being produced. So it seems trivial in this example, but it has a lot of applications where we can think about anytime I have a targeted weight or like even a targeted number of I don't know, kind of like a volume, right? Like a size. If that really matters and this product is potentially like saving lives or doing something important, we could go to companies and tell them, look, you need to change your production process because you're not hitting that targeted weight or you're not hitting that targeted volume. Okay. Any questions over anything that we worked through on that one? Where's the, oh, here it was, right? Anything that we did here? Okay, no one in the chat. All right. So one thing I do want to point out though, in this problem is, what if instead the company tells me like, well, no, we're very confident that the average plate we're producing is 45 pounds. You have to be wrong, right? And I go, well, I can say it with 90% confidence, but can I come back to them and say, well, I told you before with 90% confidence, I could tell you you weren't hitting your target. What about 99%? Well, if I want to get 99% confidence, what's the only thing that's going to change in this equation? Well, now my alpha over 2 with 99% confidence, alpha is 0.01 divided by 2. So I want 0.005 in the tail. So in order to get a smaller area in the tail, I'm going to have to use a larger z value. If the z value goes up, I'm adding and subtracting a larger amount. My confidence interval is going to get wider, right? So my guess is that at the 99% level, if my confidence interval is going to get wider, we probably get a lower bound that now 45 could be one of the true values for that population mean. I mean, because once I go to I'm pretty close already, right? 45.11. So just going out a little bit, a couple more standard deviations away, or even a fraction of a standard deviation away, I'm now at the 99% level, not going to be able to tell them that their product doesn't weigh that 45 pounds, right? Or that targeted population mean. Okay. Any questions on that? Okay. Let me point something else out here. So one thing to think about is whenever we're building these confidence intervals, we're adding and subtracting the same amount to that sample mean. So our sample mean should be smack dab in the middle of our confidence interval, right? So if I go back to this problem, I did give you some potential answers on the previous slide. Oh, there we go. I could have ruled a couple of these out pretty quickly. So if the sample mean I found was 46.5, that's not even in this confidence interval, right? 46.5 is actually outside. Doesn't make any sense. We're using that sample mean to build our confidence interval around it. So we can rule D out right away. And then this one's a little bit more tricky, but if I look at B here, 46.5 is just about 2 away from the lower bound, but it's about 3 away from the upper bound. So it's not exactly in the middle. So B doesn't make any sense for me either. So if I'm taking a guess at this point, and I don't want to use my calculator and do anything, A or C is going to be the answer, right? Now, when I actually work it out, we can determine which of those is correct, but at least there's a couple I could rule out right away, just knowing the principles of confidence intervals. Any questions on anything that we've worked up to or worked on up to this point? Okay. So we're right exactly where I want to be. So let's go. Let's use this confidence interval example file. Okay. So there's a couple different worksheets. We're going to be dealing with multiple types of different confidence intervals we can build. But today we're going to use this known standard deviation and proportion. Right? We haven't talked about proportions yet, so we're not going to do that one. But we can deal with examples where we're looking at a sample mean and we know the population variance. Okay? Now these might seem kind of weird, like how do I have the population variance and not the population mean? If you're thinking that, you're right. But that's a whole nother, that's adding kind of the next principle, which we'll probably end up doing. My guess is Tuesday of next week we'll get to that. Maybe not till next Thursday, but probably Tuesday. So, but for now, assume that we know the population variance. And this kind of makes sense like in the production process examples, because like I could know the variance on a machine, but not know what, if it's hitting that targeted mean. So let's blow this up. And I've got a bunch of, so these, I think I stripped the names, yeah. All right, maybe no, probably have to scroll over. Here they are. So there's a bunch of different schools, right? All in Division 1. And I have their male, female, and total undergraduates. I have an indicator variable that's a 1 if they have more than 10,000 undergraduates enrolled, and a 0 if they don't. Okay? So I can kind of think about things like the size of universities. So we're going to delete some of this so I can rebuild it. So we're going to delete this. Okay. And then we're just going to delete that, right? Well, hopefully, right, it's pretty easy to find kind of the average undergraduate enrollment. That's just the mean, right? I can select that variable and I've got my sample mean. Now it's a very large sample, right? I don't have every school in this data set, but I have a lot of them. So we could find the sample size. This is something we've already done too. What formula do we use to find kind of the number of observations? Yeah, that's just the count, right? So it just equals count, and I selected that variable. So I've got, essentially, you can think about my sample size is, my equation is just n, right? So my sample size, I guess I could have done this as well to make it a little bit more clear, right? Sample size is just n there. So I've got my sample mean, sample size. Now the variance that I'm going to be thinking about, right? I calculated it here, but assume that this wasn't population data. Assume that I would have to just give you that variance, right? So just assume that this was the variance that was given. Okay? Doesn't seem very practical, and it's not, but it's another issue that if we were using a sample variance instead of population variance. So for now, assume that we were given the population variance. Okay? So that's kind of our setup. Right? So we go down here. How can I build upper and lower bounds using the information I have? Well, it's really just using Excel to be a calculator, right? I want Excel, right? I can use it as a calculator, just simply plug in, if I can get my, there we go, to simply like select where I have the sample mean, the variance of my sample mean, or standard deviation of my sample means, and this z-score. Right? So how can I use Excel to find that z-score? So we did go over this, but if I know the area that I want in the tail, what equation can I use in Excel to give me that z-score? So we said the norm.s.dist was when I tell it a z-score, it'll give me the probability of seeing that z-score or anything to the left. If we use norm.s.inv, that's using a standard normal distribution. You tell it the area you want in that lower left tail, right? And it will give you the z-score that gives you that area. Well, that's essentially what we're doing with the tables, right? We knew alpha over 2, right? So we know that we want alpha over 2 in the tail. That's the probability we want. And we want to find the z-score associated with that. Well, that's what this formula does. That norm.s.inv uses that standard normal distribution, looks up that area in the tail of alpha over 2 that you've now told it, right? That's the probability you wanted. And it spits back out at you the z-score. Okay? Now notice this is very exact, right? So I said it earlier it was what? Negative 1.645. It actually isn't exactly that. You've got even more decimals, right? But once I have that z value, one thing that I think makes it easier, right, is when we enter in the lower and upper bound equations, typically we think about adding the margin of error at the upper bound and subtracting the margin of error at the lower bound. So we don't want the negative value. We just want the absolute value, right? We don't want that negative sign to be there. We just need the absolute value of that z-score. So one thing we can do in Excel, there's a couple different things, right? So one of them would be just use this function, which is ABS, which just takes the absolute value or essentially drops the negative sign. Right? So I should get the exact same z-score now, but positive. Now the other way I could have done this, and I'll do it down here. I could have used that norm.s.inv. And if I told it alpha over 2, it gave me negative 1.64. Well, if I wanted alpha over 2 in that lower left tail, what area did I also want in the upper right tail? Alpha over 2, right? I had two sides, both had alpha over 2. Well, if I was thinking about the right side of this distribution, and I wanted alpha over 2 in this upper right tail, then if I tell Excel the area to the left, which would be 1 minus alpha over 2, it will return to me the same z-score, right, but positive. Okay. So I can use that absolute value. That's usually how I do it, honestly, because that's the way I think. Like, look up alpha over 2 and then just ignore the negative sign, essentially. And that's what using the absolute value does. Or I can use 1 minus alpha over 2, and it should give me the same value. Sure enough, it does. Okay. So either way is fine, right? Now, from here, I can actually do several different confidence intervals very quickly, right? Because if I copy this down, it just keeps updating the alpha value that I'm using. And these are kind of our benchmark alphas, right? 90, 95, 99% confidence levels. So now it's really just using Excel to be a calculator. So there's like, so I'll tell you right now, and maybe this is for people who probably aren't going to be watching this, but there are equations like confidence.norm, and they work, but they're essentially telling you what your margin of error is. And I think it's much trickier to use this function than just having Excel do a little work for us. So that's why I break it down to just use Excel to find the z value, because we want to get used to how we do that in Excel to begin with. And then here, when I'm finding my lower bound, it's really just using Excel to be a calculator, right? I know that to find my lower bound, I'll take the standard, my sample mean, upper bound plus that z-score that I already found in Excel, times the standard deviation of my sample means. So what I'm going to do, is up here, I have the variance on the original variable I sampled from. So I'm going to, in this cell, put standard deviation of sample means. Okay. It's going to be over here just so we can kind of see that label. Well, the standard deviation of my sample means is simply the square root of the variance, population variance that I sampled from, divided by my sample size. Right? So I'm essentially here calculating that intermediate step, right, or that intermediate value, which was the standard deviation of my sample means. Right? Now this makes it very easy for me then to find the lower bound, because the lower bound is just, yeah. Did I go too quick? Oh, I thought you said question. All right. So to get the lower bound, I select my sample mean. I then subtract, right, that z value that given me for alpha over 2 in the tail, and then multiply by the standard deviation of my sample means, which I calculated up here. Right? So I'm just using Excel to be a calculator here. I'm not limited to 2 decimals. I can just click on the cells very quickly instead of, well, what do I round at here? And do I put 4 decimals for each value? Just click on the cells here. It's a lot easier. So now I've got my lower bound. Now, if I copy this down, this looks kind of weird. What mistake did I make? If I copy this down, what's the problem going to be? Well, if I'm trying to build 3 different confidence intervals, I'm building each one of them around the same sample mean, and they all have this same sample size. So notice when I copy this down, oh yeah, those cell references start moving. So when I look at that equation, the sample mean is always going to be the same. So I want to freeze that cell reference. So I'll hit F4 or Command T on a Mac. I want the z-score to keep updating, right? Because that's really the only thing that changes when I'm building different levels of confidence. And then that standard deviation of my sample means, okay, yeah, this guy, I want always to be using the same. Oh, I need to actually test it. You guys hear me now or no? I'll probably have to test it again. Oh, okay, there we go. We're good. All right. I don't have no idea why it does that, but. So our lower bound's getting lower. Well, how can we build the upper bound pretty quickly? So there's a couple ways you could do this. I think the easiest is, I'll show you the easiest way first. So the problem is if I just copy this over, this is going to change. But I don't want to freeze it because then when I copy it down, well, I got to unfreeze it. So the easiest way, if you want to copy something in Excel and not have the cell references change, if I highlight this, copy it, right? And I'll hit enter to get out of the cell. And then go click on this cell, and then I paste it. Notice it didn't update that cell reference. Right? I didn't want it to. I wanted to use the same z value for the upper bound. So copying and pasting it that way, instead of like dragging it over to copy it with your mouse, none of the cell references will change. Right? So that's probably the easiest way to do it. And now from here, I mean, I've got everything in there, right? Now I just, oh no, I don't. Do I? Yeah. All right, so now I just, oh wait, what mistake did I make? Well, these numbers are all the same. Exactly, right? For my upper bound, I have to add that margin of error, right? So now that okay, yeah, that makes more sense. Now I copy this down. All right, these numbers kind of start to make a little more sense here. My upper bound is getting higher as I go to higher levels of confidence. Okay? So we basically just built 3 different confidence intervals pretty quickly, right? So with 90% confidence, right? If I want to, let me make sure I can I'll just insert a column here. So if we think about what levels of confidence these correspond to, 90, 95, and 99, let's say I'm thinking about a value like, with 90% confidence here, I can say that the true population mean is not 19,500, right? Because 19,500 would be just outside of this confidence interval. But with 99% confidence, I couldn't say that, right? Because at the 99% confidence level, 19,500 is actually in my confidence interval. So it could be one of the true population mean enrollment values. And I could do this for other values too, like, if I'm thinking about someone comes to me, is the true population enrollment for D1 schools, 17,000? Well, at high levels of confidence, that's very possible. It's one of the values that's in all of my confidence intervals. Yeah. Yep. Oh yeah, so all we did was change that negative sign into a positive sign. Yep. Any other questions? Okay. So, this is kind of how we would build these confidence intervals in Excel. I think if there's anything else I want to say. So we've got proportion stuff on here. Okay, I'll show you another way you could do this as well. So I'm going to get rid of this for a second. I'm going to have the same setup, and I want to build the exact same thing. But what I'm going to do now, and I'll actually resave this file and repost it so it has kind of this additional work. I actually can do everything all in one line. Right? So to get my lower bound, I'll take my sample mean, right? I'll subtract, well, if I look at the formula, the z-score that gives me alpha over 2. Okay? Well, I said to do that, I can use that norm.s.inv. Right? I can tell it alpha divided by 2. Now I have to do one of two things, which is what? If I ignore this part, what will that norm.s.inv? It's going to give me a z-score that is negative, right? We said that was a problem. Well, if I subtract a negative, it's actually adding it. Well, that's my upper bound, not my lower bound. So I would need to either use that ABS function to take the absolute value, or I could do, we said, 1 minus alpha over 2. Okay? It's just two different ways of doing the same thing. I then need to multiply by the standard deviation of my sample means. Well, before I calculated the intermediate step, I could have just plugged this into my formula and had it in this format, right? So then I need to multiply by the square root of the original variance of the data I sampled from divided by my sample size. Okay? So there, I'm going to multiply by the square root of the original variance divided by, right, so the original variance divided by my sample size. Okay? So I can do it all on one line, and that saves me some space, right? I didn't have to calculate the intermediate, standard deviation of my sample means. I didn't have to have this extra column, and that's fine, right? I'm getting the exact same value, and I could reconstruct this entire thing, right? So what's the only thing that I really want to change? The alpha value that I'm using. So I would freeze that cell reference for the sample mean, freeze the cell references for the population variance and the sample size. Now I can copy this down, and I have the exact same thing I did before. Right? So it's just that I didn't break it down into steps. Now, can you do it this way? Yes. Do I think you should? No, because you can't see what the norm.s.dist is telling you. It's very easy then to get the signs kind of mixed, like flip-flopped, which is why I always kind of show you them first finding that z-score and then using Excel as a calculator. And even doing the intermediate step too, where you find this standard deviation of your sample means and put it in a cell here. You don't have to do it that way. I just think that it gives you kind of a clearer picture, right? We're talking with someone the other day about 221 curriculum stuff, and the idea of using Excel in this class. I was like, I think that a lot of the times, like, you can use Excel to just black box things, but you can also use it to break things down step by step, and it gives you a much clearer picture than a lot of times what you would get doing it by hand, right? And this is one of those scenarios where I think breaking it down, finding the z value for alpha over 2, then using it as a calculator, calculating the intermediate, like the standard deviation of our sample means. I just think it gives you a little bit clearer of a picture of what you're doing, as opposed to, I'm just using this formula, plugging everything. It's a little bit, you get lost in the weeds a little bit more there. Now, if I want to do the upper bound here, this is where I said probably the easiest way: highlight this, copy it, and also this is just a kind of a little trick with Excel. And it becomes more important when we start copying and doing some more things that we're doing now. If I want to get out of this cell and I click here, oh shoot, I just erased everything and it puts that cell, right? So I'm going to use the undo command, which I don't know what it is on a Mac, but it's Control Z on a PC. I'm sure if you use a Mac, you probably know what the undo command is at this point. So I'll copy it. The way I get out of this cell, just hit enter, right? Now I can go over here, paste it. The only thing I need to change, my upper bound, I'm adding that margin of error instead of subtracting it, right? Hit enter. Now I can copy this down. I've got the exact same values that I found before, okay? Any questions on any of the Excel stuff that we just talked about? Okay. I want to hold off on proportions until next class, but I do want to try. I'll introduce this here. It's not going to be like required. So the next Excel assignment, I won't post it until probably after Thursday's class. And we probably won't have covered all the material. So the due date's still going to be a couple weeks ways off, because we're covering some stuff that you can start working on it, but it's going to be a while till we get to everything. So one thing I do want to show you that we'll start using, and I don't think this will be on the assignment, so don't feel like you have to have the best understanding of it yet, but we will start using in the future if statements. Okay, so let me think of an example here. So let's use that. Is 19,500 the population mean? Okay, so let's say that's the question we have, and we have these confidence intervals. Well, with 90% confidence, is this in the interval? Well, I can see very easily that no, it's not, right? But if I want to do these checks very quickly and also have it update, if let's say, for instance, I find out, oh, the population variance wasn't what I told you, it's actually a little bit different, or I get a higher sample and I could recalculate the mean and all this would update for me, I could use this if statement and say, okay, look, telling Excel, I want to check to see if something is true. If it is true, I want you to do this. And if it's not true, then Excel, I want you to do that, right? So the very first thing we tell it, it's in that order, right? The test that we're trying to run. So what we want to know is if 19, and probably, actually, I have an extra 0 in there. So 19,500, if that is greater than my upper bound, right? If that's true, okay, then put, what would we say? So right, if it's above the upper bound, it can't be one of the true population means. So not true mean. Okay. Comma, if it's false, then I want this cell to read, oops, not that, hold on, I accidentally hit something, there we go. So comma, if it's false, right, and it's not greater than the upper bound, so that would mean that it's actually in the interval, maybe just put in interval. Okay. So it checks to see if this is true. If that value of 19,500, which maybe we know someone tells you, no, the average enrollment at university is 19,500. Well, you say, okay, well, if that's outside my interval, right? If that's greater than my upper bound, I can tell that person with 90% confidence they're wrong, right? That can't be one of the true mean values, so not the true mean, right? If this is true, then we're saying that that 19,500 is not the true mean. If this statement is false, and it's actually in the interval, then in this cell, I want the cell to read that population mean is in the interval, that 19,500 is in the interval. Now, I made a mistake here. If I hit enter, it's going to be really mad at me. Okay. So one thing that you need to tell Excel, if you ever want it to put text in somewhere, the text has to be surrounded by quotation marks, right? So if the statement is true, put the text not true mean. If the statement is false, put the text in the interval, and now we get that. Right? And the reason why this is kind of interesting, and delete my 1 0 here, is because now if I drag this down, it's going to start checking against the next confidence interval's upper bound and then the next ones. Notice 19,500, you can pretty easily see, oh yeah, it's outside the interval for the 90 and 95%, so it can't be the true mean. But at the 99% level, it's actually in my interval, so it could be one of the potential true mean values. That's just kind of a brief introduction to the if statement. We'll use it more so once we get to hypothesis testing, but we can kind of play around with it a little bit here too. And this is always like a nice when you're presenting this stuff, like if you have different values, notice I could have put the value over here, and then I could start to play around with, instead of putting the number, oh, now I don't know where it's at. There it is. I could have referenced the cell the number's in. So I'll copy this back down. Oh, I have to freeze this because I don't want that to change, right? Or no, wrong one, right? This was the cell that had the 19,500 in it. So now I'll copy this down. And now notice I can play around with, okay, well, I can see that's not in the 90 or it's not within the 90 and 95% confidence interval, but what about the value of, I don't know, 17,500? Okay, that's in every single confidence interval. I can just play around with that one shouldn't be, oops, well, that's not gonna be in any of them. All right, that's not in any of them. So, if I use a cell referencer, I could start to kind of play around with different numbers. It's pretty easy to see visually if a number is not in your confidence interval, but I wanted to introduce this idea of the if statement since we had a little bit of extra time, and I know that we're going to kind of use it down the road, or at least I'll show you some things that where I use it. Okay. Any other questions from me? So we've got that connect homework due at the end of the week. A lot of you've already kind of reached out with questions, so I think some of you got a pretty good jump on it. But try to get working on that. Make sure you get your questions in as early as possible. I'll put an online quiz up after class today that'll be due before we meet on Thursday, before class starts. And then other than that, I'll see you guys on Thursday, okay?